consider two different X matrices. The first X matrix is the one we've been working with, 2, 0, 0, 1, negative 3, 0. Let's consider the Y we originally started with, 2, 3, 4. And when we projected Y onto the column space of X, the corresponding error vector was 0, 0, 4. What it says is, if we take this new matrix X, 1, 1, 1, 1, negative 1, 0, and use the same Y the error vector looks like negative a half, negative a half, 1. And curiously, we might notice that although this error vector was optimal, it was the shortest possible error vector when projecting this Y onto the column space of X, and this error vector is optimal in that it's the shortest possible error vector when projecting this Y onto the column space of this X, this error vector satisfies a property that this first one doesn't. In this first one, the errors add up to 0 plus 4, which is 4. And in this second one, the errors add up to negative a half plus 1, which is 0. So the question is, why do the errors in the second case add up to 0 when they don't in the first case? First, I'll note that in this picture that we've been drawing, where this is the column space of X, and this is the vector Y, and this is the projection, and this is the error vector. I'm sorry, I should have used my colors, but I just wanted to point out which picture I'm talking about. Nowhere in this picture was the sum of the error vector being 0 a desirable thing or a constraint. Like, we never thought about that here, so there's no reason it needed to be true in general, right? And so there's nothing wrong with our calculations up there. The answer is not that we did something wrong. Rather, the answer is that there's something special about the X matrix here that guaranteed that the numbers in the error vector would add up to 0. And what is special about the X matrix down here is that it happens to have a column of all ones in its column space. In fact, you don't have to look that hard in the column space to find it, because it is literally just one of its columns. Okay? What do I mean by that? Remember, in that picture we just had up here, the error vector was orthogonal to any linear combination and every linear combination of X's columns. So here, we verified this earlier, 0, 0, 4 is orthogonal to this thing, and it's orthogonal to this thing, and it's orthogonal to 7 of this minus 74 of that, and it's orthogonal to negative 94 of this plus pi cubed times this, right? 0, 0, 4 is orthogonal to anything you can make with linear combinations of these two things. Similarly, this error vector, negative a half, 1, is orthogonal to anything you can make through linear combinations of this vector and this vector. Okay, that's coming from the geometry of our situation here. But the fact that we have this 1, 1, 1 means that 1, 1, 1 dotted with our error vector had to be 0. Because the error vector had to be orthogonal to anything you can make with these columns, and this itself is just one of the columns, so you can make it with the columns. Okay? That is what guaranteed that the components in this error vector would add up to 0. Remember, we've seen this before. When you dot a vector with 1, 1, 1, the result ends up being the sum of the other vector. And the way we see that here is the dot product of 1, 1, 1 with A, B, C is just A plus B plus C. But here we're being told that that's 0 because these vectors had to be orthogonal. And what that means is the sum of the components in this error vector had to be 0. So the big takeaway here is that anytime you're projecting Y onto the column space of X, and X either has a column of 1, 1, 1 in it, or a column of 1, 1, 1 can be made with linear combinations of X's columns, then you'll always have this property that the numbers in the error vector of your projection will add up to 0. Okay? So 1, 1, 1 didn't explicitly need to be one of the columns for this to be true. If I instead change my X to, 3, 4, 4, and 7, 0, 0, 1, 1, 1 is not one of these columns. Okay? But it is a linear combination of these columns. Okay? I could multiply this column by a quarter, which would give me a 1 here, and 3/4 there. And then I could multiply this by 4 over 7, something like that, right? I could multiply by whatever I would need to turn this 3/4 into 1. Okay, and these would still be the ones that come from multiplying these 4s by 1/4. My point is, 1, 1, 1 is a possible linear combination of these columns, meaning that in this case, whatever the error vector would end up being isn't necessarily that specific one, but whatever it is would have to add, the components in it would have to add up to 0 because you can make 1, 1, 1 through a linear combination of these columns. Okay, that's a big idea that we are going to use heavily when it comes to linear regression and how we revisit it through the lens of the normal equations and linear algebra. The fact that having a column of 1s in the column space of your matrix X enables or guarantees the sum of the errors to be 0. Okay. One other thing I'll say, is it only the case that the errors add up to 0 when 1, 1, 1 is in the span of the columns of the matrix X? Not necessarily, right? Like for example here, what if the vector y was 2, 3, 0? Well, then we could make it exactly using a linear combination of these columns. And so the errors would all be 0, and so they'd also add up to 0 too. So it's not the case that a 1, 1, 1 has to be in the column space in order for the errors to add up to 0. Rather, if 1, 1, 1 is in the column space, the errors are guaranteed to add up to 0, but they still could add up to 0 in other cases, depending on the relative placement of y and the columns of X.